So let's take a look at an example. And here we're looking at population growth, population of bacteria. So we have that our culture is starting here with 500 bacteria, and we want to go through and sort of make sure that we don't miss any information. After 3 hours, we're going to have 8,000 bacteria, and we'd like to start by setting up the differential equation that models this population growth. So fine, let's take a look at A. So let's choose maybe y to be our quantity, and then we have our differential equation, dy dt is going to be a constant multiple of the given quantity. So for now, that's going to be our differential equation, and we have that y of t is going to be the population after, in this case, t hours. So fine. Let's take a look at B. What is the relative growth rate? So really what this is asking us to do is to find the constant k. So we don't need to take this differential equation and solve it. We know what the solutions are going to look like. Here what we can do is assume that our population function is going to be y0 multiplied by e to the kt. And we know y0, that's going to be the initial quantity. So going back up, we have that we started off with 500 bacteria, so that's y0. And we also know that y of, I believe, 2 hours, 3 hours was 8,000, so let's fix that. Y of 3 hours was 8,000. Okay, so let's use some of this now. The first one, we can plug in y naught right here as 500. So y is more specifically 500 e to the kt, and we want to find k. So here let's find k. So we're going to have to also use this second piece of information that after 3 hours we end up with 8,000 bacteria. So on the left-hand side, we're going to have 8,000. And we have 500 e to the k multiplied by 3. So here we're going to solve for k. We end up with 8,000 divided by 500 is going to be e to the 3k. So now we want to get k outside of this exponential. So we're going to apply the natural logarithm. We also get that this value right there is just going to be 16. So we end up getting on the left-hand side, ln of 16 is equal to 3k. And so from here, k is just going to be 1/3 ln of 16. And this value is approximately equal to 0.924196. And so that is our relative growth rate. So we know k. We go back up, find the number of bacteria after t hours. So here we just want to set up the actual function itself. So for C, we have that our bacteria after t hours will be 500, which was our initial population, multiplied by e to the k. So we have 1/3 ln of 16 multiplied by t. And so that's going to be our function. We could simplify this a little bit, but for now, let's leave it as is. Let's take a look at D. When will the population reach 30,000? So here, all we're going to do is solve for when y is equal to 30,000, and we want to find t. So fine, Let's set this up and see what we end up with. So we have 30,000 is equal to 500 e to the 1/3 ln of 16t. And here we divide both sides by 500. So this is gone. And on the left-hand side now we have 30,000 divided by 500. So that's going to leave us with 60. And actually we can now get rid of this exponential. So we'll take our logarithm. So we have ln of 60 is equal to 1/3 ln of 16 multiplied by t. So now let's solve here for t. We end up getting that t is going to be equal to 3 multiplied by ln of 60 divided by ln of 16. And so t is going to be approximately equal to 4.4301 hours. So fine. That's how long it'll take for us to reach 30,000 bacteria. Let's go back up. So what is the doubling time of the bacteria? So this is a very standard sort of question for these growth questions. What is going to be the doubling time? And really the process is going to be the same for every doubling time question. So here, let's take a look at E. Really, if I want to know what the doubling time is, then I want to solve for when my quantity y is equal to 2 times the initial quantity, which really is saying solve for when y is equal to 2 times 500. So when is y equal to 1,000? So very similar to the last part that we did there, just part D. We have 1,000 is equal to 500 e to the k, where k was 1/3, ln of 16 multiplied by t. And now we're going to divide again both sides by 500. So what we have on the left is just going to be 2. Now if you think about it, that is not a coincidence. Okay, we're looking for doubling time. And on the left-hand side, we have 2 times y naught, and over here we have y naught itself. So we have 2 on the left, and this will be the same equation every time we're looking at the doubling time. So now we're going to take ln of both sides. We have ln of 2 is 1/3 ln of 16 times t. So that means that 3 times ln of 2 divided by ln of 16. That's going to be equal to t. And let's figure out what that is approximately. And we get 0.75 hours. So for this bacteria, the doubling time actually turns out to be less than a single full hour. And that's it for the first example.